Swayam Prabha. Digital India. Educated India.
Well, today what I had decided was that till yesterday we have completed the basics of the different approaches of calculating the frictional factor, the frictional pressure drop, because the other pressure drops more or less they were quite straightforward, depending upon whether there is going to be an area change or whether there is going to be a quality change, or whether the compressibility effects are quite remarkable, we will have an acceleration pressure drop. If it is a non-horizontal, we will have a gravitational pressure drop, and frictional pressure drop at all times it is going to be there. So, the thing which I had concluded in the last class was more or less we have completed the homogeneous flow model. The only thing which was left was a discussion on the denominator part. So, regarding that, since I found that many of you are not very conversant with compressible flows, so I thought I will just brush up a few things of compressible flows, and maybe I will take maximum 1 or 2 classes, not more than that, and then from there once you understand compressible flows, when we write down the momentum balance equation for compressible flows, we find that for that particular situation also denominator term comes. So, we are going to first understand the significance of the denominator term for compressible flows, and then accordingly we can understand the significance of the denominator term for two phase flow under homogeneous equilibrium conditions. You will notice as we go subsequently for the separated flow model, there also a denominator term is going to appear. It will always appear whenever the compressibility of the phases have to be considered, because it comes from the fact that V is a function of P. Okay. So, therefore, after this also whenever for separated flow or for such other conditions we get the denominator term, it will be easy for us to correlate it with equivalent useful parameters. Okay. So, I will start from the basics, some basics of compressible flow, so that maybe it may be a repetition for some of you, but anyhow more or less I will just touch upon the basics and then we will proceed further. Okay. So, suppose we take up now, whenever we talk of compressible flows, the first thing is what is compressibility. Okay. So, how do we define compressibility? Any idea how do we define compressibility of any particular substance? What is the way by which we define the compressibility of a substance? Very true. All of you are more or less to some extent it is correct, inverse of bulk modulus, the change of density with pressure and so on and so forth. Okay. So, the basic definition is it gives you a measure of its change in volume, gives a measure of change in volume under the action of this. Actually, I should have prepared a slide, but anyhow under the action of normal compressive forces. This is what is important. So, it is a measure of the change in volume of the substance under the action of normal compressive stresses on any fluid element. So, this is the thing, and what are these normal compressive forces? Now, for any fluid element at rest, the normal compressive stress is its hydrostatic pressure. Okay. So, for any fluid in rest, normal compressive stress is nothing but hydrostatic pressure. So, therefore, the degree of compressibility it can be characterized, it is usually characterized by two parameters. The first parameter is the bulk modulus of elasticity. The two parameters which characterize the degree of compressibility of a substance is, first thing is bulk modulus of elasticity, which is usually defined as, you know these definitions probably, this is defined in this particular form. So, the negative sign naturally it shows that increase of pressure causes decrease in the volume, or in other words this delta V by V, it's we know that it is nothing but delta V by V, it is nothing but minus delta rho by rho, where V is the specific volume and rho is the density. So, from there we get E equals to limit, we can also write it in terms of density in this particular form, in other words rho dP d rho. This can be one particular thing, this is one, but usually for fluid cases, apart from bulk modulus of elasticity, we prefer to use a second definition. Any idea what that definition is? We prefer to define it in terms of compressibility, kappa. With this compressibility, it is nothing but 1 by rho d rho dP, or rather minus 1 by V dV dP. So, from these two, comparing these two, you can very well understand that kappa is nothing but equal to 1 by E. Now, remember one thing, whenever we are dealing with any gaseous substance, and for a gaseous substance, whenever we try to compress it, we find that a change in pressure changes its volume and it also changes its temperature. So, unless temperature is maintained constant or unless the temperature is specified, this compressibility term has got no meaning. Okay. So, therefore, if we just define kappa, it is not very useful. We have to define the isothermal coefficient of compressibility. In other words, this is defined in this particular form, where this can be written down as del V del P at constant T. This is the correct definition, or in other words, this can be written down as 1 by rho del P constant T. I hope you can differentiate between rho and P that I have written down. Okay. And so, therefore, from here we find that for real gases which are far removed from their liquid states, for such gases usually the ideal gas equation is quite valid, for which we can write P equals to rho R T, we know it, and we know that whenever the gas undergoes any particular process, then for that particular circumstances we can describe the process in terms of P by rho n equals to say a constant k, isn't it, where depending upon the value, or rather P v to the power n equals to k, where depending upon the value of k, or rather the value of n, it depends upon the process that we adopt. All of us know it, n equals to 1 for isothermal process, n equals to gamma for adiabatic processes, and so on and so forth. Okay. So, for adiabatic processes, more or less we know that dV dP it is equal to minus V by xp or np, sorry, it is dV dP equals to minus V by np, and so from there we can very well define that your E, the bulk modulus of elasticity, this is nothing but np, and kappa equals to 1 by np. This we know very well and we can define. Now, whenever this is for fluids at rest, whenever a fluid is at rest, what happens? Its density or its specific volume, it changes with pressure. We can define it either with bulk modulus of elasticity or with the coefficient of compressibility. Whenever we define it in terms of compressibility, since a change in pressure brings about a change in volume as well as a temperature, it has to be an isothermal coefficient of your compressibility. Okay. Now, whenever a fluid is moving, now under that circumstances, what happens? Under that circumstances, we know very well, you know it from Bernoulli's equation, a very well known fact that the pressure head and the velocity head, they have to be conserved, isn't it? Or in other words, for flow problems, what we already know is, we know that P it is, or rather P plus rho u square by 2, this is equal to constant. Okay. Or we can write down that delta P in any particular flow field, that is more or less equal to rho u square by 2, which is nothing but the dynamic head. Okay. Now, we know that delta rho by rho this is nothing but equal to, okay, I will derive a little, it will be easier for you. E, how did we define E? It was limit delta V tends to 0 minus delta P delta V by V, is not it? And just like I had written it down, this is nothing but equal to this particular term, is not it? Now, we know E in terms of density, if we have to define, then E will be equal to this, I had already done, this is delta P by delta rho by rho, or it is rho dP d rho. So, therefore, we can write dP is nothing but equal to E d rho by rho. Can we write it down from the basic definition of the bulk modulus of elasticity? We can very well write down this particular equation, agreed, and we can substitute this particular dP in the dP which we had obtained from Bernoulli's equation. Okay. So, we can substitute this particular dP in the expression which is obtained from the Bernoulli's equation, is not it? And so, therefore, from here what do we get? We get that delta rho by rho, this is nothing but equal to delta P by E. This is rho u square by 2 E, or in other words, this is half u square by E by rho. Can we write it down in this form, yes or no? I am just doing basic substitutions. And what is this E by rho? From Laplace equation, any idea of what is this E by rho? E by rho, very good, E by rho, this is nothing but A square, where A is the acoustic velocity or the velocity of sound in that particular medium. So, therefore, what do we get? We get delta rho by rho is nothing but equal to half m a square, correct. So, therefore, from this equation what do we get? If delta rho by rho is very small, that means the density is not affected by pressure and the fluid is incompressible. You agree with me? So, therefore, delta rho by rho is very small, means Mach number is very small. So, now do you understand? You all of us, you had already known that Mach number, it is the most important characterizing parameter for compressible flows. This equation explains why this is so. Agreed? So, therefore, we find that in order to define the compressibility or the non-compressibility, you have to see how by how much amount the density changes for unit changes in pressure, and how much amount it changes, that can be related with the Mach number under that particular conditions. Agreed? So, therefore, we know that for incompressible flow or for incompressible gases, delta rho by rho has to be very small, okay, or Mach number has to be very small. Now, we know one thing, that if we consider that we can allow a 5% change of delta rho by rho, say even for that if we allow that 5% change of delta rho by rho, under that condition also, and if you substitute it here, then your MA, it is almost equal to 0.33. Agreed? And for the corresponding to this particular MA, the A, the velocity of sound, we know it is 340 meters per second under STP, or 340 meters per second at STP. So, therefore, this gives you, it is more or less about say 110, 112 meters per second. Do you get? So, even for a 5% change in density, we find that the velocity of flow has to be greater than about 110 meters per second in order to manifest compressible flow characteristics. So, for most of the cases, we can ignore the compressibility of the gaseous phase even, because usually under normal circumstances, we as chemical engineers or mechanical engineers, we do not go to such high flow conditions. For aerodynamics etc., it is very important. Okay. So, from this we understand why under most circumstances we can deal, or rather we can treat the gas phase as incompressible, but if you do so, you can complete the calculations, but at the end you have to show that the density changes were negligible. For any problem that you do, you can assume incompressible flow. You can do the entire problem. We will be doing a problem tomorrow which will enable you to understand this, but at the end you have to show that compressibility effects are very small. Okay, that has to be shown at the end. So, from here we find out that number 1, how to define compressibility, and number 2, why Mach number is so very important for compressible flows. The next thing for which we should find out, what is it? We know that for in order to define, or in order to quantify compressible flows, we need to know, and rather we need to know the Mach number under that particular conditions. For knowing Mach number, we need to know the velocity of flow and the velocity of sound under that particular conditions. So, now let us see how to express velocity of sound in terms of measurable parameters. Agreed? So, if we want to find out a measure of the velocity of sound. Now, suppose we take maybe any particular compressible flow. Now, when we have an incompressible fluid, okay, and in that particular incompressible fluid, we send a pressure pulse. What happens? It displaces the particles. Whenever it is propagating, it is displacing the particles. These particles displace more and more particles, and then overall all the particles they get displaced. For compressible flows, what happens? As the pressure pulse is travelling, it displaces the particles. Moment it displaces the particles move ahead, and then it increases the density of the adjoining area. As it increases density of the adjoining area, then it again increases the density of the next adjoining area. In this particular way, when a pressure pulse propagates in compressible flow, we find that more or less it propagates by increasing the density of the fluid through which it is travelling. Initially, if the density was rho, then now it is rho plus d rho. So, as the pressure pulse is travelling, all the properties they change, say pressure P to from P to P plus dP, T to T plus dt, rho to rho plus d rho. In this particular way, the pressure pulse propagates, and when it is propagating through a fluid at rest, then it also imparts some velocity to the fluid, which is much less as compared to the acoustic velocity, or much less to the velocity of the pressure pulse. If we assume that the pressure pulse is of infinitesimal strength, then we can approximate it as a acoustic wave, right, elastic wave or an acoustic wave. Okay. So, now let us see under such circumstances, let us picturize the situation. Say in this particular case, we find that the pressure pulse, it is travelling in this particular direction, maybe from the right to the left it is travelling at a velocity u. Okay. Now, while it is travelling, it displaces a particle, and when it displaces the displaced mass, it compresses and increases the density of the neighboring mass. This increases the density of the adjoining mass, and in this particular way it travels. Okay. So, now since the pressure pulse, it is travelling in this particular, from this particular direction, it has not reached this particular portion. So, in this portion on the left hand side, the fluid is at rest, it is undisturbed, it is not affected by the pressure pulse till now. So, here the properties will be P, T, rho, and u will be equal to 0. Okay. And since it has already travelled from here, here it is going to be P plus dP, T plus dt, rho plus d rho. Okay. And since it is travelling, it imparts a very small velocity du to the fluid. Okay. So, this what I have represented, it is a moving wave of say frontal area, the cross sectional area through which it is moving, frontal area A. Okay. So, we find that the disturbance, it is travelling in the form of a elastic wave or a pressure wave through the medium. Now, if the amplitude of the elastic wave, assuming that the amplitude of the elastic wave is infinitesimal, so then elastic wave infinite, then it can be, we can assume it to be an acoustic wave or a sound wave, as a result of which its velocity can be defined as A, the acoustic velocity in that particular medium under that particular conditions. Okay. Now, when this infinitesimal pressure pulse is propagating at a speed A towards still fluid at the left, so the properties I have defined as I have shown here. Now, for steady state analysis, what we can do? For steady state analysis, we can superimpose another velocity A from this particular direction. So, that what happens, your pressure pulse, it becomes stationary at one particular location, is not it? We can do it, we can superimpose a velocity A from this particular direction. Now, moment we do this, what happens? We find out that in here, if we superimpose, then we find that more or less the pressure pulse, it becomes constant at any particular location. Okay. Pressure pulse which has a cross sectional area of A. Now, for this circumstance, what happens? We find that for this particular section, we find that fluid is entering from this direction, fluid is moving out from this direction, and in this direction fluid is entering at A. This fluid is under conditions of P T rho, and the fluid is going out from this particular control volume. The outlet conditions are P plus dP, T plus dt, rho plus d rho, and here the velocity was u equals to A, and in this case it will be u equals to A minus du. Yes or no? Did you understand this particular portion? Just for performing the mass balance and the momentum balance, we want a particular control volume. So, what we do? We enclose that infinitesimal area which is by which the pressure pulse is enclosed, and that particular small area it is actually travelling. So, what we do is superimpose another velocity from the opposite side, so that that small area it becomes stationary, and then we can assume that fluid is entering into that area from the left hand side, fluid is going out from the right hand side. So, now for this particular fluid entry and out in that particular small cross sectional area under steady state conditions, we can perform the mass balance as well as the momentum balance. You got my point? So, therefore, for this particular case, let us perform the mass balance and the momentum balance and see what happens for these particular cases. Now, for mass balance, I will just draw it up once more, so that it is easier for you. Fluid is entering at u equals to A, fluid is going out at u equals to A minus du. Here it was P T rho, here it was P plus dP, T plus dt, rho plus d rho, and of course, I have already told you that the cross sectional area that is equal to A. Now, from mass balance, what do we get? Mass entering rho A, mass going out rho plus d rho, A minus du, A. Any portion you do not understand, it is very simple, you can tell me, you can just tell me to repeat it. So, therefore, we know that A cancels out, this gives rho A plus A d rho minus rho du minus du d rho. So, these also cancel out. and we get du equals to a d rho by rho plus d rho, is not it? This is the thing which we get. Now, from this particular equation there are two things that we understand. First thing is, if d rho is positive, if d rho is greater than 0, du is greater than 0, right? If d rho is greater than 0, du has to be greater than 0, agreed? Or in other words, whenever such a flow occurs, whenever a compression wave it travels through a fluid, it definitely leaves a fluid moving in the direction of the wave.
du d rho
Yes.
small multiplication of these two small terms.
You can, we will be neglecting it at the end. You can just write it down as a d rho by a by rho d rho. Definitely we will be doing it at the end, but I have just written it down. If you want, you can cancel it at this particular very beginning by assuming d rho tends to 0. Definitely we will be doing it. Okay. So, for this particular case we find that from this equation we get two informations. What is one? That definitely when a pressure pulse or a compression wave it travels through a fluid, it leaves a fluid which is travelling at a small velocity in the direction of the wave, because du has to be greater than 0 when d rho is greater than 0. This is the first thing that we observe from here. And then we know that within the framework of infinitesimal strength of the wave, we know A itself is also very small. Okay. So, this was about the mass balance. Now, let us take up the momentum balance, and we can do it in this particular page as well. If we perform the momentum balance. So, momentum balance, what do we get? Momentum in your force in minus force out equals to rate of accumulation of momentum. So, from here we get P A. If you see that force which is entering, it is P A. I will just write it down here. So, you can compare and find out, minus P plus d P A. This is equal to rate of momentum in minus rate of rate of momentum out minus rate of momentum in. So, how much momentum, mass into velocity? Mass I have already written it down, rho a a. So, it is rho a a into a minus du minus rho a a into a. If you compare this picture, this is going to be the momentum balance. Agreed, all of you? So, on simplifying this, we find that we get P A minus P A minus A d P, this is equal to again rho A square minus rho A du minus rho A square. They cancel out, these cancel out. So, finally, what we are landed up with? We are landed up with minus A d P equals to minus A rho A du. A is also, they cancel out, or in other words d P is nothing but equal to rho A du. This is the thing, very sorry. This is the thing that we get, and du, for the expression of du we can substitute du from this particular expression, isn't it? So, if we do it, then on substituting, what do we get? We get that A square, you just substitute it and you will find you get dP d rho to 1 plus d rho by rho. Okay. You can cancel out this term in the very beginning, or you can do it at this stage as well. In the limit d rho tends to 0, what do we get? A square is nothing but equal to dP d rho. Agreed? You are already probably familiar with this particular expression, although I do not know whether you had known the derivation earlier or not. Now, remember one thing, this process firstly was adiabatic and reversible. Why? First thing, the frictional effects, they were confined to the inside of the pressure wave itself. Okay? Since frictional effects are confined to the inside, so therefore, we can therefore, there were no velocity gradients on either side of the wave, and we can assume the process to be reversible. In addition, there were no temperature gradients except inside the wave. So, therefore, we can assume that the process was adiabatic as well. So, therefore, remember that we have done this derivation under the condition of adiabatic and reversible process, or in other words, this derivation was done for an isentropic process. So, therefore, putting this condition here, we can write down A square is nothing but equal to del P del rho under isentropic conditions, okay? Or in other words, A equals to root over of which you already know dP d rho at constant S. Now, for a perfect gas or for an ideal gas, as we say, for most of the conditions, as I have already mentioned, if the gas is far removed from its liquid state, we know P equals to rho R T. So, therefore, if we perform the differentiation, we find that P by rho gamma, this is equal to constant. So, therefore, A in terms of measurable properties, it is nothing but gamma P by rho, or in other words, it is gamma R T. So, by this particular process, we can first what we did, we find out how to define compressible flows. We found that Mach number is important. Now, in order to calculate Mach number, what we need? We need velocity of sound. If we can relate velocity of sound under that particular conditions with measurable parameters, it is going to be very convenient. So, the next thing which we did is we related A, or we expressed A in terms of the absolute temperature, or in terms of pressure and so on. So, we obtained the A is nothing but equal to root gamma R T. These expressions probably all of you knew from the beginning. What you did not know was probably the how we arrived. Why was Mach number important for compressible flows, and why is A equals to root del P del rho at constant S. Probably these things you were not very clear earlier. Now, whenever we define, remember one thing, the next thing which I would like to do, whenever we define compressible flows, whenever we define an incompressible, suppose water is flowing through a pipe, how do we characterize the water? We tell that its density is 1 gram per cc, it's at say room temperature 30 degrees or 25 degrees centigrade, it's at 1 atmospheric pressure, right. So, moment we tell this, we know, and it is maybe its volume flow rate is so and so and other things. So, moment we just define its temperature, pressure, density, maybe enthalpy, etc., the state of the water becomes fixed. Any point from that water, if we measure the property at any point, that is constant or that is the same. Entire water can be characterized by that property. Now, what about compressible flows? Compressible flows, at every point pressure is different, at every point density is different, at every point temperature is different. So, what to do about it? Whenever such a thing happens, we have to refer to some standard conditions. Without standard conditions, there has to be a datum with which we can compare and we can identify or we can characterize the properties. Any idea what are the reference conditions for compressible flows? What are the properties which we refer to as, because just property does not mean anything for compressible flow. Which properties? Any idea you have, whether you have heard about the name, I would like to know. That how do we, what are the standard or the datum properties in compressible flows to which we refer to the property under the present situation. You may have heard about the term. Have you heard about stagnation properties and sonic properties? Okay, we will be discussing about, you have heard about these things, isn't it? So, therefore, the useful reference conditions remember one thing, compressible fluid and compressible flows are not always the same. Okay. Useful reference conditions for compressible flows are the stagnation properties, they are one set of properties, and the sonic properties. Now, what are these? Let us define them first. Stagnation itself, it means that somewhere the fluid should be at rest and the properties under those conditions. But remember one thing, how the fluid has been brought at rest, that path is also important. For compressible flows, the path is also very important, how we have brought the fluid at rest. So, therefore, when the fluid is brought isentropically to rest conditions, then the property which the fluid has under those rest conditions, they are referred to as the stagnation properties. Usually how do we denote them? We denote them with a subscript 0 along with the property. Like pressure, the stagnation pressure is P 0, the stagnation temperature is T 0, the stagnation density is rho 0. Agreed? So, therefore, the stagnation properties are those properties they are defined as those properties those properties which are obtained if local flow were imagined to cease to 0 velocity isentropically. This means that whatever equations you have learnt in your thermodynamics for reversible adiabatic flows, all of them can be used in this particular case. So, therefore, we know certain things from energy balance. We know that more or less our say for such a type of flow, suppose we would like to write down, just I will go a little back and I would like to write down certain things, we will be using these things. For such type of flows, say maybe compressible flow, it is flowing in one particular cross sectional area, say in this particular cross sectional area A, where the curvature at the central line can be neglected. Okay. So, the properties will be varying at each and every point. So, therefore, they are a function of your axial distance. So, therefore, properties are written down in this particular fashion. The velocity is uz, the area of course, it is Az. Okay. So, from continuity what do we know? We know rho A u equals to constant, W equals to mass flow rate is constant, that we already know. A useful form of this equation is to take the log and to perform the logarithmic differentiation. From here we get d rho by rho plus d A by A plus d u by d equals to 0. Okay. And from energy balance what do we get? From energy balance, it is just the first law of thermodynamics for open systems, from which we get dq, dw we are going to neglect, this is equal to dh plus d kinetic energy plus d potential energy. Okay. Now, usually we know that the potential energy that can be neglected, because in this particular case it can be neglected. So, therefore, and the kinetic energy, okay, I will go to the next page. The kinetic energy per unit mass, this is nothing but equal to u square by 2. Okay. So, if this is substituted in the energy balance, in this particular energy balance equation, then we get dq equals to dh plus u du, is not it? So, the energy equation, remember this particular equation, this is valid even in presence of friction or non-equilibrium condition. In integral form, we can write it down as h2 plus u2 square by 2 equal to h1 plus u1 square by 2 plus q. We can write it down in this particular form, which tells us that sum of enthalpy and kinetic energy, it is constant in adiabatic flow, is not it? This term becomes equal to 0. So, therefore, we find h plus u square by 2, this is constant under adiabatic conditions. From energy balance equation we get it, you can also get it from the steady form of from the second law of thermodynamics also. You can use it and you can get it by knowing that TdS equals to dH minus VdP, is not it? By applying that also you can get it. Okay. So, therefore, we find that for adiabatic conditions, even if there is friction, even if there are irreversible effects, we know that under adiabatic condition the sum of enthalpy and kinetic energy of a fluid is constant. Agreed? So, therefore, at any particular point in a pipe, H plus U square by 2 equals to constant. Agreed? Now, if this particular fluid is isentropically brought to rest, then what happens? Isentropically means it is adiabatic reversible. So, under that condition U becomes equals to 0, H becomes equal to H 0. Agreed? H 0 is the stagnation enthalpy. Do you get my point? What do I know? From energy balance I have come to know that under normal conditions we know that the summation of H and the kinetic energy is equal to Q. For adiabatic conditions what I know, the sum of the enthalpy and kinetic energy, this particular sum, it always remains constant at any particular portion of the fluid. That means, whenever the flow is occurring from under whatever condition, at each and every cross section H plus U square by 2, that has to be H 1 plus U 1 square by 2 has to be equal to H 2 plus U 2 square by 2 has to be equal to H 3 plus U 3 square by 2. Now, at any particular point if U equals to 0, then in that case that means it has isentropically being brought to 0. Okay. So, under that condition what do we get? We get H is reduces to H 0, the stagnation property. How did I define the stagnation property? It is those particular properties which are formed when the fluid ceases to move or when a fluid is brought to rest isentropically. You agree? Do you get the point? So, therefore, we can write it down in this particular form that for all these circumstances, for adiabatic flow, this particular term, this is constant. This we can write, is not it? So, therefore, the stagnation enthalpy H 0, this is nothing but equal to H plus U square by 2, is not it? This we have got from first law of right. We have already deduced it. So, therefore, we get H 0 equals to H square plus H plus U square by 2. Now, for a perfect gas or for an ideal gas I should say, H 0 equals to Cp T 0, is not it? Okay, T 0 is the stagnation temperature, this will be equal to Cp T plus U square by 2. You agree with me? Okay. Or in other words, we can write it down, we can write down U square, it is equal to 2 Cp T 0 minus T. Agreed? We know what is Cp, gamma r by gamma minus 1. So, therefore, this U square can be written down as 2 gamma r by gamma minus 1 T 0 minus T. Yes or no? Okay. And therefore, we can write down the velocity as root 2 gamma r by gamma minus 1 into, yes, correct, which gives you u max, the maximum velocity, it is nothing but equal to 2 gamma r T 0 by gamma minus 1 whole to the power half. Can we write this, yes or no? So, therefore, from this particular equation, and from this equation, what do we deduce from these two equations? We deduce that the total enthalpy and the T0 are conserved if the process is adiabatic. Remember, for these two equations we did not put any condition of reversibility. So, for any adiabatic process we can write down the total enthalpy and the stagnation temperature T0, they are conserved if the process is adiabatic. And what about this? This gives us a relation between the fluid velocity and the local temperature under adiabatic conditions. Everything just adiabatic we are talking. Okay. So, this just gives you a local velocity, a relation between local velocity and the local temperature under adiabatic conditions, right. Now, once we have obtained a particular way of deducing or rather finding out T0. So, in the same way or rather if we just proceed further from this particular equation, what do we get? We get Cp T0 equals to Cp T plus u square by 2, or in other words we can write it down in this particular way, or we can write down T0 by T. This is nothing but 1 plus u square by 2 Cp T. Substituting Cp by gamma r by gamma minus 1, we get this is nothing but 1 plus gamma minus 1 by 2 gamma u square by r t. Yes, we have just substituted Cp, we have not done anything else. We can get it, or in other words this can be written down as 1 plus gamma minus 1 by 2 m a square. Can we write down this equation? Yes or no, you tell me. We can write it down. So, what have we done? We have expressed our local temperature in terms of the stagnation temperature, right, and we find that the relationship between the local temperature and the stagnation temperature is a function of Mach number. Okay. Now, remember, for this equation also it is just for adiabatic flow. Okay. Now, once we could find out a relationship or we could find out an expression to express T0 by T using the equations of adiabatic reversible flow, the relations connecting P to T, rho to T, we can find out rho 0 by rho, we can find out P 0 by P and so on, is not it. So, if we write them down, what do we get? In the same terms we get P 0 by T, this is equal to T 0 by T into gamma by gamma minus 1, which is equal to 1 plus gamma minus 1 by 2 m a square gamma by gamma minus 1, is not it. Same way we can write rho 0 by rho equals to T 0 by T whole to the power 1 by gamma minus 1, and this is equal to 1 plus gamma minus 1 by 2 m a square 1 by gamma minus 1, is not it. So, therefore, we find out that we are able to relate all the local properties in terms of the stagnation properties. We had started with the first law of thermodynamics for open systems. We had first considered adiabatic systems. Using that we could express, or rather we could find expressions for H0 and T0. Then we used the expressions of your isentropic conditions, and then from there we found out the relationships between P0 and T0. Okay. Now, remember one thing, that whenever a fluid is flowing, the stagnation properties, they should vary from point to point depending upon their actual properties, is not it. So, for each and every point they should have different stagnation properties. Now, suppose there is no heat transfer and we can neglect the frictional losses, then under that conditions we can say that the fluid flow inside the pipe occurs under isentropic conditions. Can we do it? We can do it, is not it. So, the thing is that if we can assume that generally what we find that the stagnation properties they can vary throughout the flow field. But if we assume that the flow is adiabatic, or rather then we find H plus u square by 2 is constant throughout the flow field. Now, if H plus u square by 2 it is constant throughout the flow field even in the presence of friction, then we can say that all the stagnation properties have to be constant along an isentropic flow. Yes or no? Okay. So, therefore, we find that for each and every position, if the condition is maintained isentropic, then under for that situation, even if the properties are varying along different cross sections, but isentropically if the properties are brought to rest under for each and every condition, then the stagnation properties will be the same. And what will be the stagnation properties? They will be the properties which the fluid will have if it started from rest in a stationary tank or a reservoir. Suppose the flow starts from a reservoir. Okay. So, from that reservoir the flow is flowing through the pipe, and in that pipe we have maintained isentropic conditions. Then in that case the property of the fluid in the reservoir are nothing but the stagnation properties. Is it clear to you? Okay. So, therefore, it is not so very impossible. The stagnation properties are varying throughout the flow, and therefore, how to find them, it is of no use. It is not that. For most of the cases we can assume isentropic conditions, and for that particular case the flow in the reservoir, or rather the reservoir where the fluid is at rest, the properties of the fluid in that condition gives you the stagnation properties. Agreed? Now, next I would like to tell you about sonic properties. Okay? And remember one thing, there is just one thing which I would like to say. If we have a reservoir through which the flow is going, then as I have already mentioned, in this reservoir it is T0, P0 and rho 0. Okay. In this particular case isentropic flow occurs. So, therefore, Q equals to 0. So, if we measure the properties here, we know the isentropic properties. And remember one thing, total enthalpy and T0 is conserved for an adiabatic process, irrespective of whether there are frictional losses or not. If there are frictional losses, then we find that T0 and H0 does not change, but in contrast P0 and rho 0 they decrease if there is friction. So, for isentropic conditions H0, P0, T0, rho 0 nothing changes. If it is adiabatic, H0, T0 is conserved, but P0 and rho 0 they decrease. Okay. Next is sonic properties. Sonic properties are the properties when Ma becomes equal to 1, is not it? So, and these properties they are denoted by an asterisk. So, they are denoted by P star, they are denoted by rho star, T star, H star, A star, everything. Okay. So, how to express this? In whatever equations we have obtained, if Ma is reduced to 1, for Ma equals to 1, we can get the corresponding P star, rho star, T star, everything values. Okay. So, accordingly these properties are attained if the local fluid is imagined to expand or compress adiabatically, isentropically till it reaches Ma equals to 1. There till the fluid is brought to rest isentropically. In this particular case, the fluid is either imagined to expand or compress isentropically till Ma becomes equal to 1. So, therefore, what do we get? T0 by T star. Simply what we do, instead of T it is T star. When moment it is T star, Ma becomes equal to 1. When Ma becomes equals to 1, it is just 1 plus gamma minus 1 by 2, or in other words this can be written down as gamma plus 1 by 2. Okay. Same way P0 by P star, this is nothing but 1 plus gamma by 2 into gamma by gamma minus 1. Same way rho 0 by rho star, it can be written as 1 plus gamma by 2, 1 by gamma minus 1. Agreed? And we know for diatomic gases gamma is equals to 1.4. So, accordingly you can find out the values of T star, P star, rho star and so on and so forth. Now, these were the important reference properties for compressible flows, stagnation properties, sonic properties. We have found out how to express the velocity of sound in terms of measurable parameters. Phi Mach number is so very important, etc., etc. Tomorrow we will be discussing about the choked flow conditions. We will be discussing how the effect of, or rather how area change influences your flow properties. We already know that whenever there is an area change, there is acceleration even for incompressible flows, isn't it? The pressure changes, the velocity changes. Okay? The velocity changes, that happens for incompressible flows as well. In this particular case, your with area, your velocity will change, your pressure will change, your density will change. So, how the situation becomes when we are dealing with area changes in compressible flows, we will find out. We will be discussing the choked flow conditions, and we will proceed in this particular manner. Thank you very much.